everyone. So today we're going to continue to talk about polar coordinates, and specifically we're going to be focusing on translating back and forth between polar and rectangular coordinates. So I just wanted to quickly remind you again, what the deal is with polar versus rectangular coordinates. So the way that you've typically talked about, if you have a point somewhere on a plane and you're trying to describe where that point is located, traditionally you've used what's called rectangular coordinates. So you would say X, Y. And we've used this so much that you don't even really think about it, right? That just seems like that is the most natural way to describe where this point is. So we talked about yesterday how, the X part of that really describes the horizontal distance, and then the Y describes the vertical distance. So you're describing where a point is by describing how far it is to the right or to the left, and then how far it is up or down. So these are what are called rectangular coordinates. You might also sometimes hear them called Cartesian coordinates. Maybe I'll just write that down. Your book uses rectangular, but another word. So if you ever hear like the Cartesian plane, it's just another word for rectangular coordinates. So the new coordinate system that we talked about yesterday was polar coordinates. So when we're graphing things in polar coordinates, we oftentimes will be using this kind of special graph paper, because this special graph paper allows you to see exactly where all the points are that are a specific distance from the origin. So how do polar coordinates work? Well, if you have a point somewhere, the way that you're going to describe that point is you're going to talk about the angle that it takes to get to that point. So if you look at kind of what direction that point is traveling in, that angle would be theta. And then you also look at what is the distance from the origin to that point. And that would be the radius, or r. And we saw that r can be negative, and we'll see some examples of that again today. If r was negative, that would mean that instead of having the point be where it is over here, it would be somewhere over here if r was negative. And so when you're writing down points in polar coordinates, you always put r first and then the angle. Although, as I mentioned in yesterday's video, I personally think you want to look actually at the angle first, because that's what kind of tells you where to go. So this is a picture of polar coordinates. So in yesterday's video, we basically just focused on graphing points using polar coordinates. And then today we're going to, like I said, talk about how you can go back and forth between between rectangular and polar. So we're going to start by talking about if you start with a point that's in rectangular coordinates, how you get them into polar coordinates. So converting rectangular to polar coordinates. So I want to start with an example, like a concrete example, and then once we do our concrete example, then we'll be able to write down like a general formula that will always work. So I want to use the same example we were talking about last time, which was the point, I think it was 4, 3. So the point 4, 3 is maybe somewhere like this. So where does that point 4, 3 come from? Well, it means that the horizontal distance to that point is 4 and the vertical distance is 3. So I'm going to draw this a little bit differently than what I drew on the previous page. So this distance is 4, right? And then on the other page, I said this was 3, and that's true. But for the sake of what we're, sorry, I forgot that, there we go. It can be very annoying to try to erase stuff like that. But for the sake of what we're doing here, I'm going to actually put that here. It's the same distance, right? So this is 3. This is 4. Okay, so we're trying to figure out a couple of things here. One of the things we're trying to figure out is the radius, the distance r. So we want to figure out what r is. So how can we find what r is? Well, we can use the Pythagorean theorem, right? So r squared is going to be equal to 4 squared plus 3 squared. So if you simplify this all out, so we get r squared is equal to 16 plus 9. So that tells us that r squared is equal to 25. And that tells us that r is equal to 5. So that's how you can find the radius, or that number r, is just using the Pythagorean theorem. Because really, like the x and y coordinates are giving you like the horizontal and vertical distances, and r is actually that diagonal distance. Okay, so how can we find theta? So this angle here. Well, again, we have a right triangle, right? So if we were to go back to trigonometry, if we were to use, and actually sine isn't really what we want to use here, you could, but let's pretend that we didn't find r yet, and all we know is 3 and 4. So what function can we use to relate theta with these two sides of length 3 and 4? We can use tangent, right? Because tangent is opposite over adjacent. So if we do tangent of theta, that would give us 3 over 4, right? Because opposite over adjacent. And so another way of saying that is that theta is going to be equal to inverse tangent of 3 over 4. So if you type that into a calculator, and in radians mode, we'll typically be using radians. You could definitely do polar coordinates with degrees as well, but I think all the ones on your homework anyway are radians, so I'm going to stick with that. You would find that this angle was approximately 0.644 radians. And so what that tells us is that the polar coordinates of this point would be equal to, so the r was 5, and then the angle was approximately 0.644. But technically, if you wanted to make this without rounding, you could also write it as 5, and then just say inverse tangent of 3/4. That would be like the exact form of this. So I'll say that, and then let me just move this over actually a little bit. So that would be, this would be the exact form, and then right there we have the approximation. So that's going to be how it generally works. If you're trying to go from polar to, or from rectangular to polar, and oops, I messed this up. Let me move these. I thought I was at the top of the page, but I guess I was at the bottom. So I'm just going to move these. And what do I want to do here? Cut. And move them down here. Okay, so I want to just kind of write down what we just did in general, because everything we just did, you can do for any point in polar coordinates. So in general, if you have a point in rectangular coordinates, where the coordinates are x, y. So this is our in general. And you're trying to figure out, what is r and what is theta. You can always find r using the equation, using the Pythagorean theorem. And so I'm going to write something here that's a little different than maybe what you expect. So I'm going to say r is equal to plus or minus square root of x squared plus y squared. So why am I saying plus or minus? Whereas like here we just said, oh, r is equal to 5, right? We didn't say plus or minus 5. So the reason is that depending on where your point is in the, what quadrant it's in basically, when sort of the combination of using inverse tangent and finding the radius might force you to write the radius as a negative number. And so we'll do an example like that in a moment, but for now, just kind of be aware that that r could be positive or negative. And so when you're finding r, typically you want to actually find the angle first. And then once you have the angle, then you can figure out whether r is going to be the plus or the minus. So how do you find the angle theta? Well, you do exactly what we did in the previous example, which is you take inverse tangent of the y-coordinate over the x-coordinate. So this is how you can always translate back and forth, or from rectangular to polar coordinates. Just make that a little better. Okay, so I want to do another example where we're going to apply this formula and basically see how this plus or minus business comes into play. So let's say that we're trying to translate the point. Let's move this up a little more. So let's try to convert the point -3, -1 to polar coordinates. So -3, -1 would be like somewhere over here. So -3, -1. So as I mentioned when we were doing that last one, I would definitely recommend trying to find the angle first, because once you have the angle, that just will really help you figure out whether r is supposed to be positive or negative. So how do you find the angle theta? You do inverse tangent of your y-coordinate over your x-coordinate. And even though you might be looking at this picture and saying, I don't quite understand where the right triangle is, just forget about that for a moment and just kind of trust this formula, and we'll see that it still works, even though it doesn't work maybe in the way you would expect. So if you type this into a calculator, you'll find that that's approximately equal to, let me see, 0.32 radians. I'll say 322 radians. So where is that angle going to be? Well, it's a positive angle, right? And so one thing that you might remember from inverse trig is that anytime you're doing inverse tangent, it's only going to give you angles that are here, right? It's going to give you angles that are between -π/2 and π/2. So when you're converting from rectangular to polar, it's never going to give you this angle. That is not going to be your angle theta. What it's going to give you is an angle that is either in quadrant 1 or quadrant 4. And then if your point is in a different quadrant, that's where the negative radii are going to come in. So the angle that we actually found is this angle. This is our angle theta. And so that means that our point is actually kind of in the opposite direction. And that's where the negative radius comes in. So when we find the radius, we're going to do plus or minus square root of -3 squared plus -1 squared so that's going to be equal to plus or minus, so square root of -3 squared is going to give us 9. -1 squared is going to give us 1, so we add those together, we get 10. And so because we can tell that the point that we're looking for is actually in the opposite direction from our angle, we can tell that r has to be equal to negative square root of 10. So here is that kind of where that radius actually goes, is square root of -10. So what are the polar coordinates of this point? Well, we list r first. So we have negative square root of 10. And then we have our angle, which was either, if you write it in exact form, you would say inverse tangent of, so -1 over -3 is the same as 1/3. Or you can write it as, I guess in that case, maybe you'd want to also approximate square root of 10, but let's just leave that for now. And then you could say about positive 0.322. So basically you'll run into the same issue if your point was in quadrants 2 or 3. It's basically just because of the fact that inverse tangent will only give you angles between negative pi over 2 and pi over 2. If your point is in quadrants 2 or 3, that's when you're going to have to use a negative r value. But I would say just find your angle first, draw it, and then you should be able to, from that picture, figure out whether r needs to be positive or negative. I think the worst thing that you can probably do when you're doing these problems on the homework is just try to blindly plug things into formulas without drawing a picture. I think that's a really good way to get the wrong answer. Okay, so now we're going to be converting points the other way. So we're going to be converting from polar to rectangular coordinates. So we'll start with an example. So let's say that we have the point, we're going to look at 3 pi over 6. So how do we graph the point 3 pi over 6? Well, we go to an angle of pi over 6, and that would be here. And then we go a distance of 3 along that line that I just drew. And so that would put our point here. So this is 3. And so this would be the point 3 pi over 6. Okay, so how would we translate this into rectangular coordinates? Well, let me actually take this picture that we have here and kind of take it out, because I think with all the circles going on, it's maybe a little bit busy. And I think if we pull it out like this, it might become easier to see what's going on. So we have our point here. And if we're trying to find the x and the y coordinates, that means we're trying to find this horizontal and this vertical distance, right? That's how we're going to find the x and y coordinates. And so really what we're trying to do is we're trying to find the legs of a right triangle. And maybe let me just color code this so it's the same. So if we have a right triangle, what do we know about this right triangle? Well, we know that the hypotenuse has a length of 3. And then we know that our angle in this right triangle is pi over 6. So how can we go from that to figuring out what the x and the y coordinates are? Well, in this case, we actually have a special right triangle, right? It's pi over 6. So you could actually just use, thinking back to the beginning of the quarter, we learned like what the different ratios were for the sides of special right triangles. But let's say you forgot that. So if you forgot how to write down the side lengths of a 30, 60, 90 triangle with a hypotenuse of 3, what you could do instead is say, okay, well, if I look at this, this triangle here, if I take sine, actually let me start with cosine. If I take cosine of pi over 6, that's going to be equal to x over 3. And if I take sine of pi over 6, that's going to be equal to y over 3. So if we're looking to find x and y, well, we can find those by saying x is equal to 3 times cosine of pi over 6. And then we can say that y is equal to 3 times sine of pi over 6. Kind of makes sense, right? We know that y is associated with the y coordinate is associated with sine, and the x coordinate is associated with cosine. It's basically like an extension of that idea that we've seen on the unit circle, but now instead of on the unit circle, we have a situation where the radius is 3 instead of 1. So what is cosine of pi over 6? Well, it's square root of 3 over 2. So it tells us that x is equal to 3 times square root of 3 over 2. So we can write that as 3 root 3 over 2. And then what is sine of pi over 6? Well, that is 1/2. So we can say that y is equal to 3 times 1/2, which is 3/2. And so we just figured out that the x, or the coordinates of this point, if we put it in rectangular coordinates, would be 3 root 3 over 2 and 3 over 2. So this is how it's always going to work. Basically, looking at what happened here, we took cosine of the angle and we multiplied it by r, and that gave us the x coordinate. And then to find the y coordinate, we did the radius, or r, times sine of the angle. So that's going to be the general kind of way of translating. So I'll write that down like we did on the last one. So in general, so if you have a point that you're trying to translate from polar to rectangular, so you have your angle theta, and you have this distance r. So basically what we just said is that the x coordinate is going to be equal to r times cosine of theta. And the y coordinate is going to be equal to r times sine of theta. And that's it. It's a little simpler for this one, I think, in terms of, I think it's easier to go from polar to rectangular than rectangular to polar. And probably really has to do with the fact that in polar coordinates, there's multiple ways of writing down a point, whereas in rectangular coordinates, there's only one way. So it kind of makes sense that it's a simpler process. Okay, so let's do one more example with this. So let's say now that we're trying to, so in this example, we'll have the point 2, 3, but when I say 2, 3, I mean 2, 3 in polar coordinates. So you have to be a little bit careful with interpreting. So, in this example, our angle was written as pi over 6, so it kind of stood out, oh, okay, like that, that's an angle, but you can have an angle in radians that isn't in terms of pi, right? So that's what it's going to be like in this example. So in this example, we're going to convert the point, as I said, to 3, where 3 is an angle in radians. To rectangular coordinates. So what does the angle 3 radians look like, more or less? Well, it's really close to pi, right? 3.14 would be pi, and so 3 radians is going to be, I'm just going to kind of guess here, but it's going to be something like very close to horizontal, so something like this. So this would be the angle of 3 radians. And then we would want to go a distance of 2 along that same angle, and that would give us our point here. So this is the point that we're trying to translate into rectangular coordinates. So I'll put that on there. So basically you can just apply the formulas that we have here. And it might seem a little strange because, again, like you don't, in the first example we did, we saw this really clear right triangle, and in this one we don't. But just in the same way that you can do sine and cosine on the unit circle when you have angles that are, not in the first quadrant, it's the same idea here. So because, if you were to take sine of 3 radians, that would still be the y coordinate of a point, right? Like it doesn't matter whether your angle is in quadrant 1 or not. The sine of an angle is always the y coordinate. And so it's really from that idea that this follows. So how do we find the x coordinate? We just do the radius, which was 2, times times cosine of our angle, which was 3 radians. And so if you type that into a calculator, it comes out to be approximately negative 1.98. And then to find the y coordinate, you do 2 times sine of 3 radians. And so if you type that one into a calculator, that comes out to be approximately 0.28. So kind of fits with our picture, right? We see that like it makes sense that it's really close to 2, because if that point was actually on the x-axis, the coordinates would be negative 2, 0. And so we have negative 1.98, really close to negative 2, and then we have 0.28, really close to 0. So you can basically just trust that these two formulas will work. And I think of the two, of all the stuff we're talking about with polar coordinates, I think this is actually probably like the most important fact to know, is how to go from polar to rectangular. Just like understanding that the x coordinate is r times cosine of theta and the y coordinate is r times sine of theta. That's just a fact that will come up not only in the context of polar coordinates, but also in other contexts. So it's definitely a good thing to be aware of. Okay, so the last thing I want to do is we're going to do just a couple of examples of taking an equation that's written either as a rectangular equation or as a polar equation, and translating it to be in terms of the other thing. So in tomorrow's video, we're going to get a lot more into polar equations and specifically into graphing them. So this is just kind of a brief introduction, but basically the main idea is that most equations that we use when we're graphing give like a relationship between x and y, right? Y is equal to 3x. Y is equal to x squared. X squared plus y squared is equal to 9. Any kind of a graph that we've been working with is some kind of a relationship between x and y. But you can also write down a relationship between r and theta. And so that will be a polar equation, and that's what we'll work on graphing in tomorrow's video. Converting equations between rectangular and polar. So we're just going to do 2 examples. These can get kind of complicated, how to convert them, and I just don't really think that's the best thing to focus on. I would rather spend more time on actually looking at how these things are graphed, because the graphs are actually pretty cool and interesting. But yeah, so let's start with an example of going from, so we're going to go from rectangular into a polar equation. So I said at a minute ago, I said how most of the equations that we deal with are a relationship between x and y. But you can have equations that are not, right? Like y equals 5. What does that look like? That's a horizontal line. So anything, like any shape that you can draw on the xy coordinate plane, you should also be able, if you can describe it with an equation using x's and y's, in this case it's just y's, but that's okay. If you can describe it using x and y, you should also be able to describe it using r and theta. And so that's basically what we're going to do. So how does this work? Well, we know from the last page that y is equal to r times sine of theta. And so what we're going to do is we're just going to replace where it says y, we're going to replace that with r times sine of theta. So we know that y is equal to r times sine of theta. So if we put that in, we get r times sine of theta is equal to 5. So this is actually already an equation that now it took our original relationship and now turned it into a relationship between r and theta. But typically when you write down these types of equations, you usually want to solve them for r. So if we solve this for r, we get r is equal to 5 over sine of theta. And another way of writing that would be 5 times cosecant of theta. So we'll see in tomorrow's video, like what it would really mean to graph that. But for now, I just want you to see that, based on the equivalencies that we established right before this, that, at least makes sense, right? That if if y is the same as r sine theta, we should be able to take any kind of an expression involving x's and y's and kind of use that key to translate it into r's and thetas. Okay, so last example of this video, we're now going to, instead, we're going to be going from a polar equation to a rectangular equation. So we're going to convert, or what word did I use here? Oops, convert. So we're going to convert r is equal to 4 cosine theta. So that's an equation relating r and theta to a rectangular equation. So in order to translate this into x's and y's instead of having r and theta, we're going to need to use some of the stuff that we had over here. So we know that r is equal to plus or minus square root of x squared plus y squared. But for the sake of translating this, it's actually going to be a lot nicer if instead of thinking of it like that, we're going to use the fact that r squared is equal to x squared plus y squared, right? Because that's basically the Pythagorean theorem. And previously we solved the Pythagorean theorem for r, but it's also true that r squared is x squared plus y squared. So in order to actually use that, that translation, we need r squared. So what we're going to do is we're going to multiply both sides of this equation by r. So if we multiply both sides by r, so by r, we get r squared is equal to 4 times r cosine of theta. So why is that useful? Like, why you might think like, oh, we could have just put in, you know, square root of x squared plus y squared here instead of doing r squared. Well, what we did here by multiplying both sides by r, that actually helps us because r times cosine of theta is going to be equal to x. So I'll remind you of why that is in a moment, but it's basically just kind of a trick that in order to kind of make things work out nicely, we can see that, okay, we want to multiply both sides by r. So r squared, like we just said, is equal to x squared plus y squared. And then let's go back to our kind of translation here. Oops, I want to go to this other one. So we know that r times cosine of theta is equal to x. So we can go in here and replace r times cosine of theta with x. So we get x squared plus y squared is equal to 4x. Now this is actually a fine answer. Like this is a rectangular equation relating x and y. But at least for me, when I look at this, I'm not like, oh, I know what kind of graph that is. You know, like typically if we're translating something into rectangular, it might be because we want to actually graph this thing and we want to know like, what does this look like? So we're going to do a little trick here. And this is going to be like a throwback to 141. So I'm going to subtract the 4x to the left-hand side. So, and I'm going to leave a little space here and you'll see why in a second. So I just subtracted 4x from both sides. So basically, maybe just to give you an idea of how we would know to go in the direction we're going, we know that when you have x squared plus y squared is equal to a number, that's a circle, right? Like x squared plus y squared is equal to 9 or something like that. That's a circle. And so, I don't know why that just happened. And so we want to kind of force this to look like a circle equation. So what are we going to do? We're going to actually complete the square. So this is going to be a little bit different from the kind of completing the square that we did in 141, because in 141 we had like a function, and in this one we actually have an equation where we can do stuff to both sides. So what we're going to do is we're going to figure out what we need to add here in order to make this part a perfect square. We're going to leave the y squared alone. That one, you know, that already is something squared. And then whatever we add here, we're going to add that same thing here. So what would we need in order to make x squared minus 4x a perfect square? Well, we would need to add plus 4, right? Because there's a couple ways to see it. One, you might just think, you know, what would this be as a perfect square? Well, it's going to be x minus 2 squared, right? That's how you would get a minus 4x. And so if you were to multiply that out, that would give you plus 4. The other way that you can do it is, you know, there's just the rule that says you take half of this number, so that would be negative 2, and you square it, and that would give you 4. And so because we added 4 to this side of the equation, we're going to add 4 to the other side of the equation. So a little different in pre-calculus, what we did was, or in pre-calc 1, what we did is we would like add and subtract 4. And you could actually do that here as well, but then you would just want to add it to the other side. So you would get the same result. So how does this, this x part factor? It factors as x minus 2 squared. And then we have plus y squared is equal to 4. And so what does this shape look like? It's a circle with a center of 2, 0, right? Because when you're subtracting when you're subtracting from x, that gives you the x coordinate, and it flips the sign, so it's 2. And then we're not subtracting anything from y, so it's 0. And then what's the radius? The radius is always the square root of the right-hand side, so it's radius 2. So, if you're rusty on completing the square, don't worry. It's literally just one example on the homework that's like this, and there's actually a video that you can watch alongside that example as well. So I wouldn't worry too much about this. Like, I'm not going to be really asking you to do more stuff like this. I just wanted to do at least like one example for you to see. And then tomorrow we're going to be, like I said, seeing how you can graph polar coordinates. So we'll actually be able to see, without translating this into rectangular coordinates, we'll be able to still see why this shape is a circle. All right, so that's it. I will see you all next time.